What are the waveforms which have that property? PN sequence, pseudo random noise, correlation function pseudo random noise is like this. One waveform. So that's why we use such signals in radar which have an autocorrelation function which has just one peak and zero elsewhere. So that the peak position will tell you how much is the delay. If you have too many peaks, you would not be able to find out which peak corresponds to delay, right? So you must have a single peak and almost zero at the rest of it. So the lot of work has gone around 1970s, 60s to find out what are those waveforms whose autocorrelation function is a central peak and zero elsewhere. And one of them happened to be pseudo-random noise, and people use that as a signal. For example, in a Mars mission that we have, we use pseudo-random signals to find out what are the distances between Mars and us, and so on and so forth. So many waveforms are there which have this property of a central peak and a zero, and one of those waveforms are used for the purpose of as a signal here to measure the value of tau. Okay. What do you do if you want to measure the velocity of the target? How do you measure velocity of the target? Plane is moving and you want to find out what is the velocity with which the plane is moving. Here use the Doppler effect. So if you send a omega frequency f, and then the return signal will have a Doppler built onto it. So you measure the amount of Doppler. So in addition to tau, you also would like to measure the Doppler shift. So you must use a waveform which will give you peak both in terms of tau as well as in terms of omega. Two peaks. I mean a peak for two variables. So this is called the delay Doppler estimation of the radar targets. So we use different waveforms for that purpose. So idea is basically simple idea how to get the signal and signal parameters embedded in additive noise. What is the best we can do? It turns out to be the match filter. Okay. These are important knowledge you need when you go to communication theory. You will do them all over again, but okay. So let us now change our mind and come to filters. So Kaushik has covered when the signal is a discrete signal and you want to modify it in terms of its frequency content, what kind of filter to use. I will do the same thing for a continuous signal. I want to modify the spectrum of this to a new desirable spectrum by passing it through a transfer function or impulse response, which will do something on the spectrum on this. You may like to filter it so that there is a noise which is a high frequency noise can be subtracted out of it. So that should be gotten rid of. For example, if the signal occupies this band and the noise occupies larger band, no use having this noise power along with you, cut off this noise power. So you pass it through a low pass filter, right? So this filter must be a low pass filter. And depending upon the signal characteristics, you may like to put a low pass filter, high pass filter, whatever filters you want. So, the category of the filters we have seen, 1 or 2 have seen high pass, low pass and band pass. The characteristics of these filters are, ideal characteristics are Hg of omega with respect to omega, some omega c value and 0. This is a low pass filter. A high pass filter will have like this, and a band pass filter will have like this. This is characteristics will have low pass, band pass, high pass. So, now what are the filter characteristics that you are talking about? One is omega c, cutoff frequency, known as cutoff frequency, and whether high pass, band pass or low pass. And also you would like these filters to be designed with some input impedance and some output impedance, and because the signal has to be connected to it, so there will be matching here. So, you want some input impedance, some output impedance, or generally putting other way around, this may be terminated by a resistance as a load, or it may be driven by a source which has internal impedance. Right? All these possibilities exist depending upon the source condition and the load condition. So, how many things are to specify on this? I will have to tell you how much is the source resistance, how much is the load resistance, what type of filter, what is the cutoff frequency, and what kind of filter characteristics you want. All these are to be specified. So, we cannot make tables for all possible values of omega c, R1, R2 and so on and so forth, and for high pass, low pass, band pass and all this. So, is there any way of making a filter design which is called a prototype filter design, and once I know the design, I can do any problem you want for any values of R1, R2, any type of a filter and any cutoff frequencies. So, all the filter design is centered around designing the so called prototype filter. In the prototype filter, we make the assumption that the resistance level, this kind of things, is equal to 1 ohm. By omega c is always taken to be equal to 1 radian per second. And we only design a low pass filter. The impedance level is 1 ohm and the cutoff frequency is 1 radian per second, and it is a low pass filter. If I tell you this design, I must be able to convert this design to any impedance level, any cutoff frequency and any filter type. Is that possible or not? Yes, possible, very simple. These filters are made by resistance, inductors and capacitor. The impedance level depends upon the values of the inductors and values of capacitors and values of resistors. If I raise all these values of this parameter by some factor, the impedance level also goes up. So, for changing this to some other impedance level R, all R's will be, resistances will be multiplied by R, inductors will be multiplied by R, and capacitors will be divided by R, right? If I do this, you give me a filter designed for 1 ohm, and same filter I change all the values with this algorithm, and then I will get a filter with impedance level equal to R. So, there is no generality lost by designing only for R is equal to 1 ohm, because very easily you can convert it to any other impedance level.